So you already have those slides on Avenue for those that would like to take notes. Well, like we didn't discuss virtual memory yet, but everything else we discussed. Because I'm context switching, so let's refresh our minds a little bit. After we discussed the control path, the data path, the ISA, and then pipelining, we had one lecture that I give you the bigger picture of what might be after pipeline, right? We said this bird's eye view lecture where we said, okay, there are some observations about pipelining, like if pipelining is in fact increasing throughput, the IBC, can I really make it deep pipelining by increasing the number of stages? Or can I horizontally replicate the number of pipelines, which is what we call superscalar, right? And then we said also, while superscalar has its own limitations, then there are other flavors of superscalar, VLIW or EPIC, based on whether you do things at the compiler or at the hardware. And then we said, even if you do all of this complexity in a single core, you are able to extract very limited parallelism out of the program itself, because programs naturally have dependency among instructions. So architects came up with the idea of, okay, if I cannot really extract parallelism across instructions of the same application, let's do it across applications. And then to do it across applications, there were main two ideas that we had in this bird's eye view lecture. Do you recall any of the two ideas? Yeah, this was a while ago before the midterm. Yeah. Yeah, well, simultaneous multi-thread or multi-threading in general. That's correct. So multi-threading means in the same core, I replicate some of the hardware components to enable multiple threads to work on a core, and a thread is basically a process or an application on its own. This was, and we call this thread level parallelism instead of ILP, instruction level parallelism. If you remember, we said pipelining and out-of-order scheduling, all is in fact, or even superscalar is doing instruction level parallelism. It's exhibiting or exploiting the parallelism among instructions of the same application. But across applications or across threads, we call this thread level parallelism. And then there was another, well, moving forward, what we currently have in all machines, in addition to multiple threads, what else do we have? Something that all of you already know. Multi-core, right? Yeah, it's multi-core. We have multiple threads, and then we also have multi-core, right? And this was the bigger picture of the trends in computer architecture. But we never really went down into every single one of them and said, okay, how does it really work? What are the details? I just wanted to give you this bigger picture, first of all, to get the holistic view, and also to align with the concepts you cover in the lab, in mainly lab 2. Good. So now we're going back to this bird's eye view lecture, and we're going to visit some of those concepts in more detail. And we start by superscalar, and hopefully by tomorrow or on Friday lecture, we start the out-of-order. Good. Again, the superscalar right now, we spend a lot of time with caching and DRAM, which was mainly this block, right? And then we're coming back to the CPU, right? So the main things we're going to discuss in this lecture, or the main headlines, is that this idea of instruction level parallelism, how to exploit it, and then some of the problems with superscalar that we already mentioned very briefly back in this lecture, and then some of the alternatives that we also cover in a high level detail. Okay, so what we had in our pipelining lecture so far is this pipeline data path and control path, right? So we started from single cycle, and then we sliced them into multi-cycle, and then we pipelined them, right? Can you recall some of the issues we discussed with pipelining? Like if I end up deploying this, what some of the challenges that I might face? Yeah. Yeah, the hazards. And the hazards are due to the dependencies that we have among instructions. Those hazards, if I try to address them in this circuitry, what did we add? Stall logic, that was one of the things. And there was another piece of circuitry that we added. Bypassing logic, thank you. So basically, we added a bunch of wires, muxes, to be able to bypass the data from a stage to a stage. And we also added stall logic that if I cannot do anything, then I have to stall, right? And these two were the main challenges we faced in pipelining, both from hardware complexity and also it lowers the ideal IBC, instruction level and instruction per cycles of the pipeline, right? And just refresh your mind, for pipelining, the ideal IBC was, what was the value? the ideal IBC. If again there is an observer that is sitting at the end of the pipeline, how many instructions I see every cycle? Yeah, just one, exactly. So IBC is one, and average cycle per instruction is also one. But then we said this ideal IBC you almost never achieve, regardless of how many stages you have in pipeline, because of those dependencies, those logics, and those bypassing extra hardware overhead, right? Good. Great. So we also discussed some of, well, the single stage or the single wide or non-superscalar. Usually people refer to architecture as a scalar processor. Well, a scalar versus superscalar. For a scalar processor that has only one pipeline, there was always the assumption that every single stage at every cycle is only only executing how many instructions? Like, well, maybe even going one step back. In a like a multi-cycle or single cycle, it wouldn't matter, but without pipelining, how many instructions I achieve or execute for all the stages at once? Just one, right? So if I don't really do any pipelining, there is only one instruction that exists in any of these stages at once, right? There's only one across all of them. What did pipelining add? What did pipelining add? Is that now I have an overlap, ideally, right? Such that we had the observation that those hardware circuitry are different, and an instruction will either be here in a fetch or a decode or execute. It cannot exist in all of them at any time, or even in two of them at any point of time. Then why I don't leverage this hardware circuitry? And then we said, okay, if an instruction moves from a fetch to a decode, you can start fetching another instruction. So we said pipelining ideally would have how many instructions at every stage at any time? Yeah. Yeah, well, totally, that's correct. The pipeline depth. If you have 5 stages, then you have 5 instructions in all the stages. But per stage, how many instructions do you have? 1, right? So instead of having a 1 total, you would have n total, where n is the pipeline depth. And for every stage, ideally, it would be executing 1 different instruction, right? But at the end, you're still limited by 1 instruction at a time. And this was one of the observations we made, that we said, if totally I can execute n instructions for the whole pipeline that coexist in the pipeline at any cycle, then if I have deep pipelining, which means I increase n, the number of stages, I would be able to execute more instructions. That was one direction. The other direction would be if I replicate my pipeline, right? Remember we had this nice visualization of a figure that, for example, instead of having only 1 pipeline, I would have, let's say, 2. Then at any point of time, at any stage, how many instructions I'm able to execute? 2, if you have 2 wide, right? And then in total, instead of, if you have an n1, if you have an n deep pipeline, both are n deep, then instead of 1n, you would have 2n, right? So you are really increasing the number of instructions you're able to execute. And this is the main idea of a superscalar processor, right? The impact of this is that if there is an observer that is sitting here, for a non-pipeline processor, it will see 1 instruction every, here I have how many stages? 5. So it will see 1 instruction every 5 stages, or in general, every cycle, sorry, every 5 cycles. Or based on how many cycles you have, it will see 1 instruction every this n number of cycles, right? So it's 1 over n. But then if you pipeline those n stages, you will see 1 instruction every cycle. That's why your IBC is 1. Now, if there's an observer sitting here, if this is too wide, then you will see how many instructions every cycle? Finishing 2 on a steady state, because if instead of finishing 1 here, you in fact are able to finish 1 from every pipeline, so you finish 2. If you have n wide processor, you'll be able to see n instructions every cycle. This is why we said the IBC, the ideal IBC of a superscalar processor is in fact n, right? Instead of 1, you move it to n, from a pipeline to a superscalar, because I'm able to finish ideally n instructions every cycle. Good. Great. So how did we manage to do this? Well, replicating the pipeline. Let's see, for example, just as a typical example, if I want to replicate something like the ALU, just to show you that this is the main topic of this lecture. All what we said right now is we have already discussed. But then how this is being implemented. If I'm replicating the ALU, for example, in Maxim, you did set up the number of execution schedule stages to, you did vary it, which means you really replicate your scheduling stage or your execution stage. If you add another ALU in the RTL or in the design, then the problem is that you don't only add the ALU, but you also have to add all the dependency and shift logic that's dependent there, right? Because I might be able to forward from here to here, but I might also be able to forward from here to here, right? You see that? So, and this is also something we gave the number roughly back then, which is the number of bypass logic instead of being order of n. Right now it becomes order of n squared, right? Good. So assume again like two instructions, this is like if we have two wide. So what do I need to do if I want to replicate everything? You need to fetch two instructions, decode two instructions, execute two instructions, and then access the register file or the data cache. Well, first of all, here while you are decoding this, you need to access the register file for the two instructions, execute them, and then maybe if both might be memory instructions, you might want to access the data cache twice. And then finally, you might want to write back to the register file twice. So every single stage want to be replicated twice if it's a 2 wide. If it's a 4 wide, then I need to replicate 4 times. If it's n wide, then I need to replicate n times. Good. So why this is first of all something that we already have in our machine, so it means it has a performance benefit, is because from the programs themselves, like if I take these two instructions, for example, these two instructions, do they have any dependency among them? Not at all, right? I'm adding R1, R2 putting to R3, and then adding R4 and R5 putting into R6. So they're completely independent, which means from a program perspective, nothing, if you have the hardware support, nothing is preventing them from completely running in parallel, right? Not one after the other in the pipeline. So if I have a 2 wide processor, then in reality, these two will start together and finish together, right? That said, let's say if I take these two instructions instead, I change it R5 to be R3 right now. What would happen? There is a dependency between them. It's a read after write dependency, which means in reality, if I have a 2 wide processor and I start fetching this one and then decoding it, I would realize this one has to wait for this one. And hence it cannot move forward until this one really at least does the execution and then do the forwarding. So you need to have the logic that does the stalling and then the forwarding, the dependency check, right? And then they will not be truly running in parallel, right? So in that case, that 2 wide superscalar or in general any wide superscalar wouldn't behave ideally, right? Because again, there are dependencies. And then you start realizing, well, if I expand this example just to check the dependency, how many dependencies do I check? It depends on how many instructions I'm able to fetch at a time, which is basically the wideness of your processor. If you have 2, then I really need to check 2 dependencies, the destination of this one with the 2 sources, and then the destination of this one with the 2 sources, right? If I have 3, then in reality, I need to check this one with these 2 and with these 2, this one with these 2 and this, like basically you have a total of, well, 6 checks, right? And then if you have 4, then you have 12 checks. You can basically see how the number is going to scale, right? And all of this is just checking really the arithmetic read-write dependency. It does not even check for the load use case. Like there is a load instruction that is loading something to the memory, and then another instruction is going to use it. Good. So if we take an example pipeline, so up until the midterm, we'll be able to fill in something like this example here, which is a single, like a scalar pipeline, right? If I want to add it to be a 2 wide superscalar, how to achieve this? Well, based on how many wide you have, you will be able to fetch as many instructions in parallel as you can, but you still need to check all dependencies. Between these 2 instructions, apparently there are no dependencies at all, right? And for that case, you can really execute all of them in parallel. And then, well, the same thing for these 2, well, if we don't have any dependencies with the remaining ones. And then, as you can see, simply I can really execute 2 at a time, right? Make sense? Now, if there are dependencies, if I start really saying, okay, assume that there are dependencies here. Let's say, well, what is the original one? Okay, so let's start putting some limitations, right? So here, this is assuming, for example, you are able to access the memory board or you are replicating your data cache, right? Either, because both are load instructions that will require to access the data cache. Correct? Makes sense? You need the read board of the data cache because both are load instructions. In reality, even in high performance superscalar processors, the ones that you might have in a recent laptop, no one is really replicating the cache. It's very, very expensive to add, right? Even not replicating the number of read boards in a cache. So even with a superscalar processor, you still have a limitation that the memory stage is in fact not replicated. If that is the case, what type of hazard do we call this? If you only had one memory and then two instructions and trying to access it on the same cycle, what is the name of this hazard? Yeah, structure hazard, right? Because there is a hardware circuitry, the two are trying to access it at the same cycle, which is this one. What do I do with the structure hazard? Well, structure hazard, nothing. In fact, you can really bypass it. So you need to stall, right? For that reason, I'm stalling here in the record stage such that I enable the memory to be shifted by one cycle, right? This is basically the first dependency we have here. The second one is assume instead of making this R14, which is completely independent of these instructions, I want to change it to be R4. Okay, so if this is R4 instead of R14, then right now the add instruction want to read this register 4, which is going to be written by the load instruction. What did we name this thing? We named this dependency a specific name. A load use case, right? This was the last question that you really had in your midterm, right? So load use is a very, very particular corner case that still people up to the moment struggling to really high its latency. And the reason for this is that you want to read something from the memory while you read in the execution stage. So bypassing does not really work, right? As we said in detail when we discussed pipelining. For that reason, I need to stall this instruction, right? Until, first of all, this is a third load. So why I'm also really delaying the memory stage here because I need to wait, right? And then I need also to stall this add instruction until I manage to bypass from the memory to the execution, right? So for that reason here, I'm stalling the add instruction such that I manage, after the memory directly finishes, I'm able to read R4 directly from the memory, right? So to be able to do that bypassing, I need to do that stall, right? Make sense? So you observe here that the number of stalls are larger because the add, because of the two wide superscalar, started immediately with the load, not after, one cycle after if it was a single scalar pipeline, right? That's why it needs to wait a little bit more time here. And then, well, something also we know from the in-order pipeline, once an instruction stalls, everything afterwards stalls. That's why these two are stalled. And finally, if I make this load, well, address is needed as R8 instead of R18, then there is a dependency between this one and this one. When does the load instruction need the R8? That is at which stage? It's like a quick pipelining review. For this instruction, if this is R8, when does the load ray need this instruction at which stage? Decode. Yeah, but when you really need it, yeah, you do access the register file in the record stage. But when do I really need the value? At which stage? Yeah? Yeah, okay, so in memory stage, okay, what? Execute, because, yeah, exactly. This is used to calculate the address, right? And for that reason, you need it in the execution stage to take that value, add it to the offset, get the address, and then use it to access the memory to obtain the data and put it in R9, right? So you don't need this at the execution stage. And for that reason, I'm delaying it by one cycle such that I am able to really bypass from the execute to the execute, right? So as you can see, Superscalar, as far as you know how many stages you have and what dependencies you have, you can end up solving the problem exactly using the same pipeline stuff that we have discussed earlier. Okay. Questions? Yeah.
You were saying we can only store in default stage, so underneath editor line.
Yeah, okay, here. You mean here?
Yes.
Yeah, let me think. Well, in reality, that is true. I stole this one here. Well, and once this stole, in fact, this one should also stall. So I would change that figure to B. Something like this. This is B. This is decode. This is execute. Yeah. Okay. Any other question? Yeah. Because we assumed that I don't replicate the data cache nor the read port of the data cache. So you only have one data cache, but you have two instructions that try to access the data cache on the same cycle. So it's a structured hazard.
Not the second load, the third load.
But even for the third load, if you think about it, if I don't stall it, it will end up, the memory stage will end up being here, aligned with this one, because this is still a load as well, right? So still also need to access the memory. So there are in fact three instructions, one to access the memory, but not in the same cycle. These two are in the same cycle, but once this is delayed, these two will end up being in the same cycle, right? Yeah.
Does this assume that there are two read ports on the instruction cache because we're able to fetch?
Yeah, that's an excellent question. So we assumed we managed to really fetch. I will come into that point right now. How do we really manage to replicate the fetch stage without having two reports? That's a part that we have detailed slides, but assume for this right now that they don't really compete into the report of the fetch stage. Thank you. So one question to you is why it might be illogical, and it's a high level question. Even if it's Superscalar, we said it's because it's expensive, but there is another reason that why it might make more sense that I don't really replicate the read ports of the data cache or even the data cache itself, even if I have a Superscalar processor. I mentioned the cost as one reason, but can you foresee another reason that might be in fact based on your knowledge about applications and what you have done in lab 1? Any guess? I have a hint, but I will not say the hint, and then I will let it as a bonus mark. And then if I said the hint, it is just like a normal free question.
Maybe read after write.
Read after write request.
And if they assign at the same time, they'll become.
Yeah, but read after write requests would also apply to arithmetic operations, right? Here we're talking about why we don't replicate the memory stage, like the data cache or the read port of the data cache. Right? And these two are not, in fact, read after write. Both are trying to read from the memory, right? Yeah.
Is there a problem if they're trying to read from the same address at the same time?
Well, reading from the same address at the same time, it will not be a problem, but that's not. I mean, generally, you might want to read from the same address or different addresses, but yeah, it will not impact whether you should replicate or not. Yeah.
What about writing the same address at the same?
Yeah, well, if you have a separate read port and write port, then you might manage to do this, which generally is the case for a cache. Yeah. That's why I'm focusing mainly of all of our reads than what you would do, right? Yeah.
I think if you have a conflict in cache, you will stall more cycles than you stall like this.
Yeah, but this is if you only have one read. We're assuming both might be hit in the cache. I mean, from the pipeline perspective, we said earlier that all the complications we discussed in cache lectures, whether it's a mess or a hit or it's completely abstracted here. So assume I access a module called cache, it gives me the read. How does it handle it? I don't really care from a pipeline perspective, right? So the problem is that two want to get something from the cache on the same cycle, right? So with the hint, okay, so from your analysis of applications in lab 1 and from what we discussed earlier, or maybe even before this, another hint. So which instructions you think are in fact in real need, or which instructions would really cause this structure hazard at the data cache? Are all instructions would cause that? Which instructions will cause that? Yeah. Which one? Branch instructions? Well, we're trying to access the memory, right? So branches don't access the memory in reality. Loads and stores, right? So loads and stores are the only instructions that would cause a structure hazard in the memory. Because remember, and we said this multiple times in the pipelining lecture, all instructions access the memory, the instruction memory in the fetch stage, but only according to the RISC philosophy, only load and store instructions are accessing the data cache in the memory stage, right? Does this hint give you any idea why it might make sense not to really replicate the data cache? Yeah.
Be a racing condition where you right and read at the same time.
Yeah, well, but what if I replicate the board? I mean, there is a dependency check between reads and writes. So it's an orthogonal problem to what we're trying to discuss. It's an existing problem that really caches need to care about, but it's more related to coherence. That, like, if you want to read and write to the same address, then how you handle the order, right? Hopefully, again, we would have a lecture about that. But forget about this complex corner scenario, like knowing that only memory instructions will need to access the data cache. Does it tell you anything why it might make more sense not to replicate it? Yeah. Yeah, correct. And the reason for this is usually how many memory operations I would have in a program. This is not 100%, 20%, 15%, like 30% of instructions are memory. Everything in average case, well, everything in architecture goes back to how does it impact the total execution time? Again, Amdahl's law and the iron law of making the program fast, the common case fast. If only a fraction of the instructions are accessing the memory, what is the possibility that part of this fraction, two are trying to access the memory at the same time? A very small fraction, and I'm okay really making them stolen. I don't want to pay the cost of replicating the cache. If this was happening 100% of the time, even if the data cache was in fact costly, people would replicate it. Because we do replicate the execution units, right? We do sometimes some machines do replicate the floating point dividers even. Because you might really addressing programs that would have a lot of floating point division. It all goes back to what makes your common case fast. If the case is common, you'll pay all the cost to really accelerate it. If it's not common, then, well, does it worth the cost, right? So the reason, in addition to the fact that, well, cache is costly, is also this scenario does not happen a lot of, like most of the time in real applications. Good. Okay, good. So superscalar CPI, we said, well, if I have n wide superscalar, then the CPI is 1 over n, and my IBC is n. We said this is ideally, but there are also a lot of costs paid to stall dependencies and also bypassing logic. So let's take an example to calculate, and this is a performance calculation example similar to what we had in pipelining. Assume ideally you know your CPI is 1 over n, but then you want to account for some of the costs. Let's say, for example, a branch penalty cost, which is the control hazard, right? The third type of hazard we discussed. Assume I'm telling you that 20% of your program is branches, 75% of them is taken, but you have no explicit branch prediction. If I say you have no explicit branch prediction, what does it mean? How do I handle branches? Yeah, but flush them when I turn out to be wrong. What I mean, like remember in the pipeline, if this instruction was a branch, I fetch, decode, execute, memory write back. I want to fetch another one here, but I only know whether I'm taken or not after the execution. Which one do I fetch now? If I don't do any branch prediction, the default baseline case, which one do I fetch? Which one? The next one, right? Like the one directly after that program counter plus 4. That's the default case, right? And this is also what you had in the exam, right? So by default, if I state there is no branch prediction, we said in reality there is a prediction anyway, which is because the common case is that you just do program counter equal program counter plus 4. So as if you are predicting that that branch is not taken, right? Then you bring in the next one. So if I'm telling you that 75% of the branches are in reality taken, does it mean that you are correct 75% of the time, or you are wrong 75% of the time? Wrong 75% of the time, right? Because I predicted not taken, because I just very executed the subsequent one while it ended up being taken. And then assume that the branch penalty, which is the flushing cost, is 2 cycles. And we already discussed in the branches why it's 2 cycles. Then I want to calculate the actual CBR or IBC in that case. If I have no superscalar, if it's a scalar pipeline, so it's a single pipeline, then the ideal IBC is 1, right? Then 20% are branches, 75% of them I'm wrong, and I'm paying an extra 2 cycles, right? So in that case, my CBI cycles per instruction, so being 1, it becomes 1.3, right? Which means I have 30% slowdown only because of this branch block, right? And this example, we had a very similar one in the pipelining case. Now we want to solve it if we have a 2-way superscalar. If you have a 2-way superscalar, first of all, what is your ideal CBI? 1/2, right? So it's 0.5, which is this one. And then, again, what is the extra cost? Is 0.2, 0.75, and then multiplied by 2, you end up being 0.8. Right now, this 0.3 that was part of a 1, it was 30% slowdown in case of the scalar pipeline. It becomes a 60% slowdown in case of a 2-1, right? So you see that the impact of hazards started becoming dominant if you increase the number of them, right? Because you need to store, this will store, and what is the reason for this? Here I'm storing only 1 pipeline, here I'm installing both, right? This is why, in fact, the cost is double. Good. If you have a 4-way, well, you end up, in fact, with 100%, more than 100% slowdown, right? Yeah.
But it didn't slow down only faster, so it's still faster than.
Yeah, it would still be, yeah, that's a good point. Remember that here, this slowdown is in fact an issue. So we're comparing to something that is baseline, right? So this baseline here is 1, this baseline here is 0.5. So this doesn't mean that, in fact, superscalar is worse than a scalar pipeline. It means that the cost of really handling an overhead compared to the ideal scenario is larger, right? Yeah, so that's a very good observation. Doesn't mean at the end, superscalar is worse than a single pipeline, right? Well, there are scenarios that you might end up, are there scenarios that you may end up being worse? I need to think about it, but at least this doesn't make that argument, right? It just says the cost you need to pay to handle your dependencies or hazards is going to become larger. Good. Okay, so again, let's stop here and we continue this tomorrow then. Okay.